Hallelujah. Hallelujah. All right, guys. So let's start without further ado. Let's start with the textbook questions. So let's start with the. So any questions? And that includes also 33 from yesterday, because I hadn't yet taught power, so you might have had a bit of a problem with 33. So Aditya first.
Can you please take up 28 on
First.
2?
Whoa. Aditya, you raise your hand and then we'll say, yes, Aditya.
Can you please take up 28 on 242?
So 38?
28.
38? 28, you said? I cannot hear. Can you chat here? Okay. Why don't you chat, guys? Okay, so which one you want me to? So 28? But that was it was almost 2 days ago. Okay, Max. Madav, 27. That was like 2 days ago, guys. I asked you yesterday. Anyway, Max.
Oh, no, you didn't ask us for these ones yesterday.
No, but I asked, do you have any questions? No?
This was on the homework from yesterday. And
from yesterday? This is from yesterday?
Yeah.
Really?
Yeah.
What did I give you? Yesterday. I did not give you 34 to 38?
You gave us that and you gave us 242.
Really?
Yeah, you gave both of them.
Okay. All right.
So,
Okay.
And I have more questions.
Okay. All right. So 28. Hold on a second. Just chat.
Okay.
Put 28. Okay. So 27. Okay. What else? Anything else from the textbook? 33. Okay. So 33. All right. 34, 38. You're good. 38. All right. Okay. All right. So let's start with these here. So I'll give a second here. I will share. All right. So sharing screen. Zoom. All right, so let me set up this on the side, on this. Okay. All right, so let's start with 27. The graph illustrate the finding, blah, 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 blah. So 20 West means 20. Madav, all of them, A, B, C, and D?
Sir, I think you have the wrong question.
It's on a page, 242. Okay, oh, this on power, right? Oh, okay, now I get it. Sorry. Okay, yeah, okay. All right, I'm there now. Okay, so 27. All right. 613 kilogram mass is placed on a forklift. It can generate. Okay, what is the constant speed? Okay, so this one here. So let's look at 27. So what do we have here? We have a certain mass. And there's a forklift here. So of course, the forklift exert. No. Air Siri, no. Okay, I'm gonna put this on the other side so I don't. There we go. So it's the lift right here. And then what else are we having on this? Of course, it's the weight. All right. And so this mass will go up, right, a certain distance, which we don't know, I guess, right? Yeah, so what we want to find is we want to find the speed. Okay, we know the power, and that's the power of the lift, which is 950 watts. Okay, so I told you before, whenever they ask you to find the work, find the power, they always mean the minimal work required, the minimal power required, okay? So the minimum work required here to lift this up is a lifting force that is equal to the weight. You need just a little bit more, just tiny more to get it going. But once you get it going, That's fine. So the minimal power here, so what you need to understand here, you need to understand that the lift has to exert a force that is equal to the weight, all right? Now, let's look at this here. So the power of the lift is equal to the work done by the lift over delta T, right? Now notice here that there's nothing about like the speed here. But let's play with the equation as much as we can. So this is like lift times the distance over which the lifting force is applied, times what? Cos of, well, of course, the angle between the lift and the displacement is 0. So this is 0 here over delta T. So of course, this one here is 1. And where you're left with this. Now, if you're very, very clever here, you're going to see that I can put it as such, right? And what is this, guys? What's that? What is this? Yeah, raise your hand. What is that? Yeah, Ditya.
Velocity.
Yeah, that's the speed. All right, and of course it's going to be constant speed because we want to lift this. So the lift has to exert just a tiny bit more than the weight, but once it gets going, it can reduce the force to that of the weight. The inertia, of course, is going to move up. So that's the constant speed. So what you notice here is that you get this. Now here, of course, this is going to be 2 mg times v, power lift. Right, and then you just isolate for the speed. Right, that's it. Okay. All right, Madav, you good for that? Okay. A couple of things here. Another formula. So remember here, the power is work over delta T. It's also equal to this here. Okay, it's also equal to that. Provided that the force is in the same direction, right? So provided F is same direction as delta D, all right? Okay, so that's another formula sometime that may be useful. I remember in one IB exam, was it last year or 2 years ago? It was really, really hard to do the problem using like the definition of this, but it came like really, really easy if you use this here instead. So, yeah, so that's a formula that you may want to remember too. Okay, so let me see here. We had 28. Okay, so now I understand. Okay, 28. All right, so once again, 28, you play with formulas here as much as you can before like putting values. So here you have a certain amount of water, right? So water here, all right, and you're pumping this, all right, over a distance of a height of 92 meters. The flow rate, so the flow rate here is 75 liters per second. And each liter of water is has a mass of 1 kilogram. So if I turn this into mass, right, mass flow rate, this is equal to 75 kilogram per second, right? So everyone is okay with this? So what's the power required? Okay, so once again, it's the same thing. You need the minimal power. The minimal power to be provided by the pump has to be equal to the mass of the weight, sorry, of the water, right? So that's the minimum here, all right? So here you have the weight and you have the force from the pump, okay? And it has to be like the same here, at the very least, okay? So let's put this here. So the power here will be the work done by the pump over the time. Now this is going to be equal to the force provided by the pump times this, right? Times cos of 0. And then over delta t. So far, so good. Now, the force by the pump has to be equal there you go. So force by the pump here has to be equal to mg delta t. This is 1 here over delta t, all right? Okay. Now, I want you to sort of, there's 2 things that is constant here. And in this case, it's g, the gravitational acceleration, and delta d. Now, I'm going to put this on the side here. And now I'm going to ask you, like, what do you think this is? Jeffrey, your mic is on. Do you have an answer? Jeffrey Song? Jeffrey?
No
there?
clue.
Jeffrey? You have a
No.
Yeah,
clue.
Ernest.
Flow rate.
Yeah, Ernest?
It's the flow rate.
Yeah, that's the flow rate. That's the mass per unit time. So this is nothing else but the flow rate here, m over delta t. That's 75 kilogram per second. So you just put this all in, and you're gonna find what the power, minimal power required for this pump. You good? Did anyone else want cut out, or is it just me? I don't know. Yeah, I just mute everyone. Okay, I did. Yeah. All right, good. So 33. Okay, so now, so we're back to latent heat here. So 33. So on page 33. Okay, so 33. So 33. So feel free to give me a shout if there's something you don't understand, because I don't always look at the screen. So ask me for 33. Max, do you want to do both A and B? Yes, okay, you can talk. I said this for me too, because, okay.
Yes.
All right, so, okay, good. So what's the heat given off by the heater to the liquid? Okay, so what do we have here? We have the heater, right? And it's this. So of course, let me see here. Okay, and you have the time. Well, you know that the power given off by the heater is equal to the thermal energy given off by the heater, which is absorbed, of course, by the liquid. Okay, of course, here you always assume like everything is perfect. There's no loss and everything. So everything that thermal energy given up by the heater goes into the solid here, right? So you can sort of figure out. So A asks you to figure out like the thermal energy given off by the heater, and it's just going to be this, all right? Time delta t, of course, you have to change this into 60 seconds, and then you just plug the values in. All right, so times 60 seconds, and I'll give you like 12,000 joule. All right, so that's the power given off by the heater. Sorry, I made a mistake here. It's not P, it's Q, right? So Q, all right? And B, what is the heat capacity of the liquid? Well, so we're looking for this. Well, we know the formula. The formula is this times this. You're given the mass, right? So you're given like the mass here. You're given also how much thermal energy is being absorbed. And then you know the final temperature, so 80 minus 20, so 60 degrees Celsius, and you just plug this in and you find this specific capacity. Is that okay, Max? You good? Okay. 38. So 38. 38. We'll ask me for 38. Max? Okay. So 38. So it's a multi, it's like the same problem as I did like yesterday, more or less. So you have ice here. And the initial temperature of the ice here is minus 15 degrees Celsius. It's placed into a pan, heated to a liquid, right? And then to vapor. Okay, so it's a little bit long here. So what happens here, there's two change of state, liquid and then steam, right? So steam, liquid water, and then steam. For this question, you need the specific capacity of steam. So I don't know if it's given in the textbook. Is it given in the textbook, guys? The steam, the capacity of the steam.
I looked it up.
It's not given in the textbook. So you looked it up. So was it your problem, Max, that you didn't know like the specific capacity of the steam? Max? No?
I think I just might have not formulated the equation properly.
Okay, well, let me show you like the equation here.
All right.
So the final temperature, I'll put like this as TT here, right? Right. It's what is it? So it's 115 degrees Celsius. Okay. So you want the total amount of heat required. So once again here, you need to raise the ice from minus 15 degrees Celsius to 0 degrees Celsius. And then you have to melt it. And then plus the liquid water here, H2O here, liquid, from 0 degrees Celsius to 100 degrees Celsius. And then you need to vaporize it. So boiling or vaporize. Okay, so it has to go from water to steam. And then finally, when it's in steam, you have to increase the temperature from 100 degrees Celsius to 115 Celsius. All right. So if you put all this here, it'll be like the mass, the specific capacity of the ice. It's going to be like, so it goes up by 15 degrees here, right? So 0 minus 15, so 15 degrees Celsius. The melting will be the latent heat of fusion of water, right? That you find in your book, times the mass. Then here it's this times like the heat capacity of a liquid, right? Times 100 degrees Celsius, right? And then you need to put the latent heat of vaporization of H2O, which is also in your book in the one table. And then finally, it'll be like you have to bring like the steam from 100 degrees Celsius to 115 degrees Celsius. So it'll be an increase of 15 degrees. All right. And I think the specific capacity of steam is not given in the book. What did you find, Madav? What's the heat capacity of steam?
1970 kilojoules per
Just
kilogram.
give me a digit. What is it?
1.97 kilojoules per kilogram.
So 1.9 kilojoule
Per kilogram.
per gram or kilogram?
Kilogram.
So 1.9 kilojoule. Oh, that's a lot. So 1.9 kilojoule. So something like that? Is that it? Is that correct?
Sorry. It's just
1.9. Oh, there's an additional 1.9. So this, right? This?
yeah.
Yeah, okay. Yeah, so use this. Are you good, Mr. Max? And the mass, of course, is whatever the mass is given. Max, you're good? Okay. Right, sometimes you have to do a bit of research. Sometimes they don't give like all the informations. Okay, so let's go to the more challenging ones. So, blah, 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 blah. So this one here. So, questions. Hope you work on that. Yeah, Max.
Could you do 18 and 19?
Okay, so 18 and 19. All right. The solution are they given?
The answers are posted, but on the solution sheet, those two
Yeah,
are
yeah,
not.
it's not
So.
given. Yeah. So 18. All right, 19. Any other one, guys? So 14. You want me to do them all? 14, 17. Okay, Elena, did you check the answer in the back, Elena? Elena, come. Oh, 17 is not there, right?
Yeah.
But 14. 14.
No,
You check 14 and you still have a bit of a problem?
Yeah.
Okay, all right. So 14, 17. Okay, what did you have to do? 14 to 19? So you want me to do 14? So only 15, you got it right, guys? Okay. You got 16 too? Very good. You got 16.
But
Okay.
no, I have to look at the sheet for 16, but then I realized I was wrong. So
Well, you want me to do 16? You don't want me to do 16.
I looked at the sheet and I like found it out, so it's okay.
You understand?
Yeah.
Usually it's 16. That's a little bit of a problem. Okay, so let's start with 14. So let me sort of share here. And if you haven't attempted the problem, I would suggest you just don't look at it because there's no point. You're not going to learn. You're going to see someone, you're going to see a guitar player playing the guitar, and it's not going to help you like learn how to play the guitar. So you can mute me. No, you cannot mute me. But anyway, you can mute your own speaker. Okay, so and you can decide not to look at your screen. So number 14. So let's see here what we have. So we have a 5 kilogram object. It's made up of iron and aluminum. It takes, so that's a total here. It takes 504 kilojoule to change object temperature. So the initial temperature is this to this here. Of course, the change in temperature is gonna be 140. Okay, is that correct? Yeah. So what's the mass of each part? So what are you looking for here? What's the mass of each part? Okay. So let's look at this. So if you look at the thermal energy, total thermal energy will be equal to the energy that goes into the iron part plus the thermal energy that goes into the aluminum, right? Now, if you put like this, so it's the mass of the iron plus the specific capacity of the iron plus delta T plus the mass of aluminum times the specific capacity of aluminum times delta T. Now I can factor out delta T because it's the same. All right. And once again, I know this part here, I know this part, I know this part, I know this part. Okay, so what you have here is that you have one equation and you have two unknown. Well, you know in math that you have to have another equation to solve for this. Well, what's the other equation coming from? Well, it's coming from the fact that you have the total mass of the object. So what it means here, it means that the total mass of the object, which is 5 kilogram. Well, the total mass of the object is the mass of the iron plus the mass of the aluminum. So you know how to do this. You isolate for 1. So let's isolate for, I don't know, mass of the iron. Doesn't really matter here. It's going to be this minus this. This is going to be like 5 kilogram minus this. And then what you do is you just put it back in here. And then you solve. So you're going to have like everything there. All right, so if I put it here, you're going to have like 5 kilogram minus this, right? CFE plus mass of aluminum times the specific capacity of aluminum times delta T. And it's just a question of isolating for the mass of aluminum, okay? So don't forget to distribute and collect the like terms, blah, 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 and that's it, okay? So that was 414. Are you good for this, Elena? Are you good?
Yeah, thank you.
Yeah? Okay, I cannot hear you. Yes or no?
Yes, thank you.
Yes, okay, good. It's Elena, right? It's not Elena, right?
Yeah.
Yeah, all right, sorry. Okay, now you want 17. 17, so let's look at 17. An aluminum calorimeter. Okay, a calorimeter, it's a device that measures how much thermal energy is being released. That's what a calorimeter is. There's an example of this in your textbook. So on page, if you turn to page 270, there you go. No, 271. Well, it's different types. You have to, this is called a bomb calorimeter. This is also a calorimeter here. Someone that would be safe in a high school setting. This one, you wouldn't find this in a high school setting. But basically what it does is that it measures how much thermal energy is given off, let's say, an exothermic reaction, an explosion, or you want to know how much energy content there is in a potato chip. So you put this in a bomb calorimeter and you burn it to the ground. You burn your potato chip to the ground, and you record how much thermal energy is being released, and then that will still tell you like how much calorie content there is in this potato chip. Okay, so aluminum calorimeter of mass contains. Okay, so let's see here. So here. So there you go. So this is water here. This is aluminum. So mass. Okay, so the mass of aluminum is 400 grams. So we'll put this into kilogram. The mass of water is 200 grams, so 0.2 kilogram. So the initial temperature, of both, because they are at equilibrium at first, is 18. When a block of nickel, okay, so it's the same, this is the same question that I did as my example. So here, this is a block of nickel here, and you put it into this. And I guess you want to find the mass of nickel. So the initial temperature of nickel is 80 degrees Celsius. All right, and then you close everything, and the final temperature of this whole thing here, all right, the equilibrium temperature is 28 degrees Celsius. Okay, so it's a thermal exchange problem, Alina. So what we have here is that the thermal energy in the hotter body goes into the colder bodies here. The hotter bodies, of course, is the nickel, and the colder bodies here is both the aluminum and the water, right? And then you put like everything in. So here, this is like, so you're looking for the mass of nickel, right? So the mass of nickel times the heat capacity of nickel will be equal to TF minus the initial temperature right? So initial temperature, right? So I'll put like here, whoops. So TF minus the initial temperature of aluminum equal to mass of aluminum times the heat capacity of the aluminum. Delta T will be exactly the same for both because the initial temperature is the same and final temperature is the same. So what I'm going to do here is I'm going to factor out delta T. If you don't follow me, like just let me know. TF minus TI. Okay, and it's just a matter of isolating for the mass of the nickel. So you put everything on the other side. Right, so it's going to be over this. TF minus TI here, so it's like, it's a minus here. So it will be like 28 degrees Celsius minus 80 degrees Celsius. So of course you're going to have a negative sign here, but that's going to cancel with negative sign right here. And here it goes from 28 degrees, sorry, from 18 degrees to a 28 degrees, so 10 degrees. That's it. That's all what you isolate. And I put on the website, I put also the specific capacity of nickel. Is that okay, Alina? Are you good?
Like you didn't give us the answer for question 17 though.
Oh, I didn't give the answer?
Yeah.
Is that why?
Yeah.
It's not in the back?
No.
No?
I think it's on there.
Is it on there?
Yeah, I think so.
Yeah, it's on the bottom here. It's on little here. You can hardly see it. But the mass of nickel is what, guys? It's 0.0.52.
It says 0.52.
Is that it? Is that good, guys? I can put the calculation here, but is it good? Anyone? Anyone? It's good, Max? So you did it? Okay. So 0.52 kilogram. Okay. If this is the only answer you wanted, Elena, you could have asked me first before going through all this. Good. All right. So 18, 19. So 18. All right. So 18. So let's look at 18. Okay, so ice cube. All right, so let's see here. So 18. Where are we? So ice cube of mass 40 is from the freezer compartment for with cement to a styrofoam cup. Okay, so that's the styrofoam cup here. Containing 120 of water. So 120. Okay, so let's put here. So the mass of liquid water here. I'll put like H2O for water, for liquid here. It's 0.2 kilogram. You got the little ice cube here. Ice. So the mass of the ice is 40 gram. So that's the mass of the ice. The initial temperature of the ice is -8 degrees Celsius. Okay, transparent cup containing water. Okay, so the temperature, initial temperature of the water is 98.5 degrees, so it's pretty warm. Okay, so what we want is we want to find the final temperature of this whole thing. Ignore any heat loss to the cup and the surrounding. Okay. All right. All right. So so once again here, so we'll ask me for 18. I don't know who asked me for this, but anyway.
It was me.
Okay. Okay, so it's a thermal energy exchange here. It's a heat exchange problem. And And since we're not given like specific capacity of styrofoam cup, so we don't consider styrofoam cup. Okay, so so it's just going to be the water and the ice. Okay, so the colder body here is what? The colder body is of course like the ice, and the warmer body is the liquid H2O. So what do we have here is we have this. So we have like the ice here, right? This thermal energy here will be going into body of water here, okay? All right. Now, the first thing, so what you want to do, so hopefully here you want the ice to, I don't know why I don't put, you want the ice to melt. So the first thing you want to do is, of course, to warm. So the warm water here will make sure that the temperature of the ice goes up to 0 degrees Celsius. Now that you have like at 0 degrees Celsius, the ice melts into water, right? At 0 degrees Celsius. And now you have this much, this 40 gram of ice that has been turned into water. Now you have to warm it up to the final temperature. All right, so here, this is the water that has melted, not the whole water, the whole water that's melted. Of course, the whole water also have to reach equilibrium here. So from 0 degrees Celsius to the final temperature, right? So, so this is what you do here. So let me sort of put it here. So here, the ice here. So you have like warming ice. Okay, so from -8 to 0 degrees Celsius, plus, because I don't have.
Should the other side be H2O because you have two sides of ice?
What's that?
Shouldn't the other side be QH2O because you're
Yes. Sorry. What did I do? Yeah, you're right. It's the other way around, right? It's the hot. Sorry, you're quite right. So this is the. All right. So the hot is the H2O. Yeah, very good. So the water, I'll put it like water here. So let me put water. Yeah. All right, so water. And here it'll be like the ice, right? Plus, of course, the amount of ice that gets turned into water, right? So, and then, so once, so you have like the melting. And then finally, you have the warming melted ice, right? From 0 degrees Celsius to the final, oh, you want the final temperature, right? Right? Okay, so use this. So here it's going to be like the mass of the water. So let me call this like mass of the water right here. All right, so it'll be the mass of the water times the heat capacity of the water times delta T, so TF, minus the initial temperature of the water. Okay, this is going to be equal to the mass of the ice times the specific capacity of the ice times, so it goes from -8 to 0, so there's a jump of 8 degrees Celsius, plus the mass of the ice, right, times the latent heat of fusion, right, of water, plus the mass of the, I know it's no longer ice, right, but it's liquid now, but it's the mass here, times the specific capacity of the water, because now it's been turned into water, times the TF minus 0 degrees Celsius, right? And then you plug all the values in. So mass of water was 0.12, so 0.12 kilogram times 41, 80 joule per kilogram per Celsius. TF minus 18. I think it was 18. No, it was 95. So 95 degrees Celsius. All right, and then this is equal to the mass of the ice. I can factor out the mass of the ice, so I will do that in a second. So if I factor out like the mass of the ice, this, right? And then the specific capacity of the ice, I don't remember what it was. I think it was this, something like that. Times 8 degrees Celsius. Okay, plus the latent heat of fusion of water, which is 3.3. So 3.3 times 10 to the 5 joule per kilogram. Plus now the ice has been turned into liquid, so it's the heat capacity of water, right? Times TF, right? Because 0, 0, right? And it's so you change, of course, the mass of the ice here is 0.012 kilogram. And you just isolate for TF. So it's a little bit long, but you isolate for TF, it's just math. And then you're gonna find, I think that it's about 50.3 degrees Celsius. Okay? Are you good? Should the thermal energy go from water to ice? Where from water to, yeah, that's what, yeah, I'm sorry. Yeah, that was like before. Yeah, I apologize here. It's the hot is the warm water. Yeah, so I apologize about that. Is that okay? Now, there's something like tricky about this. Let's say, okay, so there's a warm water here. How do we know that there's enough thermal energy to actually melt the ice, right? Let's say like the water was warmer here. Perhaps you put it in and there's not enough like thermal energy to melt the ice, right? Perhaps it stays as ice. So how do you go about knowing this? Well, you pretend that the ice doesn't change, okay? It doesn't change state. And then you find your final temperature. So basically, like here, you wouldn't have like those two terms here. So those two terms would not be there. Okay, those two terms would not be there. Oh, it's lagging. There we go. Those two terms would not be there. You figure out what the final temperature is. And you find out the final temperature is greater than 0 degrees Celsius, then you know that there must have been a change of state, because ice cannot have like a temperature of 10 degrees Celsius, okay? So that's one way you can sort of figure out like, okay, is there a change of state? Is there enough thermal energy to guarantee a state of change, a change of state? You pretend there's no change of state, you do the calculation. If you find the temperature that the substance cannot have, all right, like a temperature whose state of substance cannot have, then you know there's a change of state. Okay, so 8, so what was that? 19. Wow, 19. So I'm doing it all for you guys. So number 19. A solar heated home has a tank containing blubber salts in the basement. Its purpose is to store 2.8 times 10 to the 9 joule of heat energy and can be heated from 22 degrees to 50 degrees. The melting point of blubber salt is 32 degrees Celsius. Has specific heat of fusion. The specific heat capacity in a solid state is this, in liquid state. So calculate the mass of blubber salt required to store the heat. All right, so what you want to do here is you want to know like how much thermal energy should be absorbed by this salt. So to store how much? To store 2.8 times 10 to the 9 joule. So this is your salt right here.
Wait, sir, it's a 9?
Yeah, it's a 9.
Oh, okay. Never mind. Then I got the answer right, because I thought it was a 4.
Oh, okay. All
So
right.
my answer is
yeah,
10,000
it's a 9
times
here.
less.
Then you said like Q, and Yeah, you start from what? Like you start like solid, right?
Yeah.
And then like melting, right? And then liquid. Is that okay? Right?
Sir, you pranked me so hard. That looks so much like a 4.
Like this one?
The one on the website, yeah. On the
Oh,
it looks like a
website.
4.
You mean on the sheet?
Yeah, on the sheet. It looks kind of like a 4, so that's why my answer was off by a
19.
factor of 100,000.
Okay. I
Yeah,
don't
I
see.
got it now.
Anyway. Okay, guys. So any questions? Well, if you don't have any questions, you don't have a homework for today, if provided you've done these. So these are a little bit like more difficult. So if you went through this, you're pretty good. And especially if you got like number 16, it's good. Usually that's the question like people ask me. So I'm surprised no one has asked me for 16. In 16, there's the heat capacity of the eggs. So that's very good. So they don't give the specific capacity, they just give the heat capacity of the eggs, right? So it's just times 5 times like 5 times the mass. There's 5 eggs, so times the mass of the eggs times 5. So that'll be the thermal energy. And so be very careful about like the loss here, right? So, okay. All right, so as I said, like we're done. There's on the website, there's a sheet that you need to download and print if you need to print it for tomorrow. If you want to, well, you're gonna write on it. So, but if you have an iPad, you can write on it like on the digital file. But if you don't, make sure you print it. Okay, and tomorrow we'll be done. Energy will be done, and next week we'll start electricity. All right. So questions? All right, so there's no question. I'll stay for another 5 minutes here if some people wants to ask me some questions. Till then, I'll see you tomorrow at 10:30. Okay, bye-bye. God bless everyone.